Okay. Hello, Mr. Harry. Are you right?
Yeah.
Today we're going to look at this count and save problem. Count and save. So let's start with the first number 1. Right? So when n equals 1, when given this integer n, we need to say it's 1, right? That's the base cases. So how do you say 1? How do you count and how many ones are there in this 1?
1.
So it's 1, 1. Okay? So 1, 1 turn into 1, 1. So how do you say this?
11.
No, count and say how many ones?
2.
2 ones. So 2 ones. Right? So it becomes 2, 1. Look. So how do you count and say this one? Like that.
1, 2, 1, 1.
Well done. So 1, 2, 1, 1. So it becomes 1, 2, 1, 1. Okay? And how do you say this?
3 ones, 1, 2.
Okay, that's a good point. So you count and say from the left. So you not merge them together. It's 1, 1, 1, 2, 2, 1. Got it? So 1, 1, 1, 2, 2 ones. That becomes 1, 1, 1, 2, 2, 1. Okay? Got it? So let's n equals 2, n equals 3, n equals 4, n equals 5.
Yeah.
For example, if we want to solve n equals 5, so what information do we need to get before we solving n equals 5? So before we get this string, right? We need to return a string. Before we return this, we need to attempt what kind of information? How do we get this number?
By count and say sequence, n equals 4.
Well done, exactly, n equals 4. And in order to figure out n equals 4, what do we need to do?
N equals 3.
Exactly, and then coming back to n equals 1. So what kind of algorithm coming to your mind? Like fn, let's say fn returns the answer. We need to get this fn minus 1, and then fn minus 2, and fn minus 3, and here f1, which is we already know is 1, right? So what kind of algorithm is this? Fn, we need to call fn minus 1 to get the answer. What is this? In general, if we have a function fn, and then it needs to call fn minus 1, and in fn minus 1, it needs to call fn minus 2. So what is this? The one we start with r. Calling itself, what do you call it?
Recursion.
Recursion, yes, well done, recursion. Thank you, Ryan. Recursion. Well done, okay. So now we can just apply recursion only, right? So the thing is that we need to count and say, for example, like that. So we need to count how many ones, look, how many ones of it and how many twos of it. So we can use a function called group by. We talk about that, right? Group by. Iter2 is called group by. So first of all, let's start with define fn. So for any recursion, we need to define the base case, right? So we have to tell the computer at some point, how do we solve the very basic problem? Like Fibonacci number, f1 equals 1, right? If we don't tell the computer f1 equals what? If we just say, okay, fn equals fn minus 1 plus fn minus 2, what happened? The computer will recursively calling itself, but it doesn't know how to solve the very basic case. So the problem will recurse itself into minus infinity, which means the problem never gets solved. So if n equal 1, return 1. Okay, now this is the base case. So we are telling computer, okay, when in n equals 1, we don't need to recurse anymore. We know the answer, which is 1. Right? Otherwise, we put this answer into a list. Okay? And for ij in iter2 group by, previous answer is a. So a equals fn minus 1. Here, look. This is recursion, calling the previous number, right? Because you said we want to solve fn. The previous answer is fn minus 1. Look. So we need to group by. For a equals 1, 1, 1, 1, 1, 2, 1. Okay, so we need to group by this answer. This is the previous result. So we group by this. We group by. We're using the group by function, and then you group by continuously groups. So that's 2, 1. So you return a key and a group. Points to the group. And here is the 2, 2. And here's 1, 1. Okay? I will be the keys. J will be the iterator. So we need to convert this iterator to a list and then get the length. Get the length, let's 1, 1. Okay? answer dot append. First of all, we want to append the count. How many of them, which is here, right? So how many of them is, first of all, we convert to a list. Bless you, list.
Thank you.
And then we get the length. List J, get the length, and then we turn it into a string. And answer dot append I, right? Okay, or we can merge these here. Answer dot append start converting to a list, converting getting the length, converting a string plus the I, and then return. This answer is the list. How do we convert a list to a string? Which function are we using?
Join.
Join, right now. So we join by empty string. Join answer, and that will be it. Right? We don't need to put a cache here, right? Why is that? The cache is optional, right? Because fn only depends on fn minus 1. So fn, for example, fn, any fn is only used once. Make sense? Look, f3. In order to calculate f3, we need to know f2. In order to know f2, we need to call f1. And f1, we know this answer is 1, and we come back, right? We're going back, we run back. So any fn, we only use once. So we don't need to put a cache. Fibonacci number, we need to put a cache. Why? Look, f4 equals f3 plus f2, right? f3 equals f2 plus f1. So do you see why do we need to put a cache? Here, f2 here, f2 here, right? So it means that we need to put a cache, otherwise f2 might be calculated over and over again. Alright, but here, look, it's just single branch. f2 only calculate once, so we don't need to put a cache.
Yeah.
The key thing today, takeaway here is goodbye. Yeah, goodbye. What does goodbye give us? 1, 1, 2, 2, 3, 3, 3. What does goodbye? If we go by this, then it will tell us 1, which is a group of 1, 1, right? 2, all string, okay? 2, 2. And 3, 3, 3, 3. We can implement the group by ourselves, but this is the very convenient method. 1, 2, 3. So the keys will be the unique element in that group, continuous. And the values will be an iterator to the actual group. Okay?
Yeah.
Okay. We use the list group to convert to a list, and then we get the length. So we know how many, this is the part of count. And say, count and say, the element is this. Yeah, the element is the group in that. Okay, and then we recursively calling the previous one until we got the f1. Okay? Okay, what have you learned today?
So the count and say is like you basically saying like the number and how many of the numbers. So like for example 1 1 1 2 2 1, there's 3 ones.
Mhm.
So and 2 twos and then 1 1.
Mm.
So it'd be 3 1
Mm.
2 2 1 1.
What kind of algorithm can we use to apply to solve this one?
Glue by.
And what's the algorithm called? We're solving a smaller size of problem, and then what's that?
Recursion.
Recursion. Yeah, recursion basically is we're solving smaller size here. Right? Look, a equals fn minus 1. So because we need the fn minus 1 results to count and say it. And these fn minus 1 recursively calling fn minus 2, fn minus 3 until we reach f1, right? Okay, suppose we are given this n is positive, okay? If we given this negative number, it doesn't make any sense. So we can just say, we can put here, if n smaller equal than 0, then return nothing, okay? Just return nothing. Just to avoid this function throws errors, right? Yeah, look, if we don't have this, if we calling f minus 2, what happens? If we don't tell the computer to check the n, if it's negative, f minus 2, right? Then you will call fn minus 3, right? fn minus 3, calling fn minus 12. Minus 12, minus 5, minus 6, minus 7, minus infinity, because the computer calling is without solving any kind of problem. So that's why the n needs to be positive. Another way we can just put assert here. We just double check n is bigger than or equal than 1. Okay, assert n bigger or equal to 1. The complexity and spec complexity, this is a bit complicated. It's all 4 to the power of n divided by 3. Okay, we're not going to details today here because it's too complicated. So fs plus t equals fs plus ft. If the last digit of s is not the same as the first digit of t. Make sense, right? So look, f 1, 2, 3 plus, okay, 4, 5, 6, right? You count and say this 1, 2, 3, 4, 5, 6 is the same as f 1, 2, 3. Count and say 1, 2, 3 plus f 4, 5, 6, right? Easy, right? Easy to understand, right? If the last digit of s is not the same as the first digit of t. Make sense? Yeah? So from that point, we'll be able to understand a little bit more about the time and space complexity. Okay? That's it for today. Bye-bye. Bye.
Nice.
Hello, Mr. Ryan, all right? So today we're going to look at these numbers. When n equals 1, we set 1, right? Okay, so how would you say 1? How many ones?
1.
Okay, so it's 1, 1, okay? So we turn that into 1, 1. Make sense? So that's n equals 2. How do you say this? How do you say this?
2 ones.
2 ones. 2 ones. 2, 1, right? How do you say this? You count and say how many twos?
1, 2.
1, 2, 1, 1, right? So 1, 2, 1, 1. So that becomes 1, 2, 1, 1. N equals 4. Okay, n equals 5. So how do you count and say this one?
1, 1, 1, 2, 2 ones.
Yeah, 1, 1, 1, 2, right? 1, 1, 1, 2. And 2 ones. 1, 1, 1, 2, 2, 1, right? And then these keep going, right? So given n, we need to return the string on the right hand side.
Group by.
Group by, yes, what's group by? So basically we need to group by the numbers and then count, alright? Yeah. We want to find out n equals 5. So what's the result depend on? So before we figure out what's the answer of n equals 5, what do we need to get?
Should know what's n equals 4.
Well, now we should know n equals 4. And in order to know n equals 4, we need to know n equals 3, right? Like, n equals 4 is the result depends on n equals 3, alright? And n equals 3 depends on n equals 2. So what kind of argument come into your mind? Fn, right? We need to find out fn minus 1, and then we need to find out fn minus 2. So what's this? We want to find out fn, and then fn depends on fn minus 1, fn minus 1 depends on fn minus 2. So what kind of the argument can we apply here? We want to find out fn, and then fn minus 1, fn minus 2. So what's this? Until we reach fn, which we need to know is 1.
Recursion.
Recursion. Calling itself, yes? Recursion, okay.
I know what's calling it, but I forgot how to say it though.
Okay, recursion, okay. So we can use the recursion, right? So the thing is that we get this from the fn minus 1 and then we count and save from the fn minus 1, right? So define fn. If n equal 1, this is the base case, return 1, right? This is the base case, right? When n equals 1, we return 1, think of 1, this is a string. Now we get the previous, which is fn minus 1, right? This is how we recursively solve the problem with n minus 1, smallest problem. So when we have this a, right? So we need to count it, for example, 1, 2, right? This is if a is 1, 2. Then we need to count this string, right? Alright? So how do we count it? The idea is to group by, right? We can implement a group by ourselves, but we have this group by function. So we group by the same, for example, like that, the same digit. So group by this, right? So once we group by, we know how many? 2, 1. There are 2 ones, and there are 3 twos. Okay? So for ij in group by is from iter2, group by a, right? And before that, we put it answer into a list. Group by. So if we apply the group by in this, suppose this group by a is this one, right? This is the previous result. If we group by, the I would be, it's an iterator, yeah? I would be 1, the element, the unique element in that group, and the values would be iterator to its group. So it's 1 1 something like that. But this is the iterator. So 2 2 2 2, right? So let's group by. So now we want to find out how many of them, right? So we can apply the length function to the list of the iterator. So there's 2 1s and there's 3 2s. And the unique element we know, right? Answer dot append. Right? How many ones comes from here? So we first of all convert it to star length list j. Yeah. So what does this mean? List j, converting this into a list, a length, which it gives the 2, and we convert it to a string, plus this one, right? So we just have to put an I here. Now this is how we count and say, count the numbers and say it out, right? And then return. How do we convert this to a string? How do we convert this? Look, 1 2 3 into 1 2 3. Well, which function is it? We talk about that. How do we convert an array to a string? What's the opposite of split?
Join.
Join, yeah. So return empty string dot join. This is a separator, join answer. So fn depends on fn minus 1. So we don't need to put a cache here, right? We don't need to put a cache because it's not reusing any of the results. If you want to get the fn, you have to calculate from f1, f2, f3 until fn. This is recursion, right? In order to calculate fn, we need the result for fn minus 1, right? Look, fn minus 1, suppose it's something like that, then we have to group by this, the string. Fn minus 1 is a string, then we use the group by to count. There are 2 1s and 3 2s. The reason we use the array to store each component, store each group, is that when we join it, it'll be more efficient. Because the string continuation is inefficient, and it's better we put the string into a list and then we use the join. Join is the reverse operation of split. The join, a string dot join, the separator is nothing, so it means we put it together. If we put a plus here, then that will become 1 plus 2 plus 3, something like that, right? If we put an empty string, then it will be 1 2 3. Okay, the time and space complexity, I mean, it's very complex, right? It's we're not going to go into details. It's around this, right? Time and space complexity. It depends on this fn function. We know fs plus t equals fs plus ft. If the last digit of s is not the same as the first digit of t, then we have this, then we can continue analyze it. But it's very complex. We're not going to go into details, but this is roughly the time and space complexity. Okay, so what have you learned today? And then that's it.
Number 1 is any was one. The other is 1 1 because there's the number 1 and there's only one of it.
Yeah, and then we count and say it out and forming a new string. Am I right? So what's the algorithm we're using today?
Group by and split, join.
No, what's the algorithm we're using? Recursion. What's recursion?
Calling itself.
Yeah, calling itself. Why do we need the recursion here? If we want to calculate fn, why do we need to call fn minus 1? If we want to count the fn, it depends on fn minus 1, right? So let's recursion. Fn depends on fn minus 1. Fn minus 1 depends on fn minus 1 until f1, which we know is 1. That's the base cases. For recursion, we have to define a terminal case, which is the base case. If we don't have this, what happens? Can you tell me? If we don't end here, what happens?
You'll keep going all over again.
And you will never end, right? Because look, f1, and then if you don't tell what to solve, if there's nothing to solve, you recurse into f0, f minus 1, f minus 2, f minus 3, f to infinity, which the computer don't know how to solve. At some point, the recursion, at some point, you have to let the computer to solve the very basic thing, alright? This is what the recursion is, right? For example, factorial. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, right? N factorial equals n times n minus 1 factorial, alright? Look, so Fn equals n times Fn minus 1, right? But at some point, we have to let computer know F1 equals 1, right? If we don't tell computer F1 equals 1, then computer don't know what's F1, and you will need to recurse into F0, F minus 1, F minus 2, am I right? Yeah? Then this problem never gets solved. F1 equals 1, right? Look, Fn, then it needs the Fn minus 1, Fn minus 2, and then gets to F1. Okay, the computer knows F1 equals 1, and come back to F2 equals 2. Yeah, 2 times F1, 3 times F2, 4 times F3, okay? Yeah? And then until it gets the value Fn. Okay, that's it for today. Bye-bye.
Bye.
Bye-bye.